Conditional or counterfactual logic is the formal study of conditional statements that go beyond the resources of classical propositional logic. While classical logic contains a conditional connective material implication, many conditionals in natural language do not seem to behave like the material conditional. Counterfactual logic aims to capture the logical structure of such conditionals, especially those that describe what would have been the case if things had gone differently. The need for counterfactual logic arises from the observation that ordinary if-then sentences often fail to match the truth conditions of the material conditional. In classical propositional logic, a sentence of the form if A, then B is equivalent to not A or B, and is therefore true whenever A is false, regardless of B. However, this result is often counterintuitive in everyday reasoning. For example, the statement, "If the moon is made of cheese, then Paris is in France," comes out true on the material interpretation, simply because the antecedent is false. Many philosophers have argued that this does not reflect how we actually understand conditionals. A particularly important distinction is that between indicative conditionals and subjunctive or counterfactual conditionals. Indicative conditionals typically concern what is or may be the case, whereas counterfactuals often concern what would have been the case under circumstances that did not in fact obtain. Consider the contrast between the sentences, "If Oswald didn't kill Kennedy, someone else did," and "If Oswald hadn't killed Kennedy, someone else would have." The first is an indicative conditional compatible with uncertainty about the actual facts. The second is a counterfactual conditional which seems to presuppose that Oswald did kill Kennedy and asks us to consider an alternative situation in which he did not. These two sentences clearly have different meanings and logical properties, even though they share a similar grammatical form. They also seem to have different truth values. Counterfactual conditionals differ sharply from material implication in their inferential behavior. Many inference rules that are valid for material implication fail for counterfactuals. For example, antecedent strengthening, the inference from if A then B to if A and C then B, is valid for material implication but not for counterfactuals. Similarly, transitivity from if A then B and if B then C to if A then C, and contraposition from if A then B to if not B then not A do not generally hold for counterfactual conditionals. These failures show that counterfactual reasoning follows a different logical structure from classical implication. The syntax of counterfactual logic usually extends the language of propositional or predicate logic with a special conditional operator, often written as A box, right arrow, B, or A counterfactually implies B, to distinguish it from material implication. Formulas are built using propositional variables, standard logical connectives, and this counterfactual conditional. The syntax itself is relatively simple. The real complexity lies in the semantics. The most influential semantics for counterfactuals was developed by Robert Stolnaker and David Lewis. According to this approach, the truth of a counterfactual depends on possible worlds and a notion of similarity or closeness between worlds. Roughly speaking, a counterfactual, if A were the case, then B would be the case, is true if and only if, in the closest possible worlds in which A is true, B is also true. The idea of closeness captures how similar an alternative world is to the actual world, taking into account factors such as laws of nature, background facts, and causal structure. Different formal systems of counterfactual logic impose different constraints on the similarity relation or ordering of possible worlds. Some systems assume a single closest A world, while others allow multiple equally close worlds. Some logics validate certain inference principles that others reject. Well-known systems include those associated with Stolnaker's selection function semantics and Lewis's sphere semantics. These systems differ in strength and in which counterfactual principles they validate. There are several proof methods for counterfactual logic. For example, some systems use axioms, some natural deduction techniques, and some semantic tableau. Counterfactual logic can be combined with other logical systems, for example, modal logic. Since counterfactual semantics already employs possible worlds, it integrates naturally with modal notions such as necessity and possibility. Counterfactuals also play a central role in theories of causation, explanation, decision theory, and the philosophy of science, and hybrid systems have been developed to address these applications. Central logical notions such as logical truth, logical falsity, logical contingency, logical consequence, and validity can, in principle, be defined in the same way as in modal logic. Logical truth, logical falsity, and logical contingency can, for example, be defined in terms of truth across possible world models. Logical consequence and validity are defined in the usual model theoretic way. An argument is valid if, and only if, there is no world in any model at which the premises are true and the conclusion false. From a metalogical perspective, counterfactual logics share many features with modal logics. Depending on the system, counterfactual logics may or may not have properties such as completeness and compactness. In summary, conditional or counterfactual logic provides a formal framework for analyzing conditional statements that cannot be adequately captured by classical material implication. By distinguishing between indicative and subjunctive conditionals, and by using possible world semantics with a notion of similarity, counterfactual logic offers a nuanced account of reasoning about, for example, alternatives, causation, and hypothetical scenarios. It has become an important tool in contemporary philosophy, logic, and related disciplines.